Welcome to Black Hat Windows 2K Security, held February 14th through the 15th, 2001 in Las Vegas, Nevada. The following videotape was recorded live at the conference and produced by the Sound of Knowledge Incorporated. This is videotape number 10, more technical track, active and passive fingerprinting of Microsoft-based operating systems using the ICMP protocol.
My name is Ofir Arkin. I'm, as it states here, the founder of the Syst security group. Sounds nice. It's a website carrying all my work, which you can go to and download all my previous papers. I'm also an active member of the HoneyNet project. How many of you heard about the HoneyNet project? Okay, it's cool. When I last had this talk back in October in Amsterdam, I stated that RFCs are meant to be read and followed. Well, seems that people didn't learn the lesson yet. Was expecting to see some of the stuff I have found changed and fixed, but apparently no one bothered. Why is it so important, or why is it important at all to use ICMP to do active and passive fingerprinting of operating system as a whole, and use ICMP for host detection, advanced host detection, and such activities? Well, the amount of traffic you have to use with ICMP is less than with other protocols. How many of you know Nmap? Okay, Nmap, host detection, port scanner, active fingerprinting tool, written by Fyodor. Sends 28 packets for one port in order to determine if this host is alive and whether or what is the underlying operating system. With ICMP, as I will show you, we will use between 1 to 3 datagrams only in order to determine the underlying operating system. Now you might say that, sure, we block ICMP on our firewall. We do not let any type of ICMP query enter our facilities, but remember that you have internal users. There is a slogan saying, one of the backup companies for Linux is saying, if we can ping it, we can backup it. Well, if I can ping it, I can know what is the operating system. A bit about ICMP. ICMP was defined with RFC 792 a long time ago. It's a nice RFC, 20 pages long. Later, there were some other RFCs which I highly recommend to read in order to understand host requirements. You can read RFC 1122. In order to understand router requirements for IP version 4, you need to read RFC 1812. There are two goals to the ICMP protocol. First, when a router or a destination host need to inform the source host about errors in datagram processing, and of course, probing the network for general characteristic about the network and determine if systems are alive and workable. ICMP is a controversial protocol, at least I think so. I will especially focus on active and passive fingerprinting of Microsoft operating systems because we are in a Microsoft Win2K conference. But if you will download my paper, ICMP Usage and Scanning, from my website, you'll see that I can use ICMP for various situations and fingerprinting not only Microsoft-based operating systems. ICMP messages are sent in IP datagrams. Their goal is not to make IP reliable. They report non-transient error messages. In the RFC, it states that the protocol ID for ICMP is 1. It states that the IP type of service field and the preceding bits field should be 0. If you are a router, you will use the value of 6 or 7 as the IP preceding bits value with error messages. Just remind, stick it in your head for a bit for later on. If you will look at the ICMP protocol, a regular datagram will be a combine of a type, you can see that here, of a code field. The type specified the type of message we're using. We have query and we have error messages. The code field specified a subtype. We have some ICMP messages which has a couple of few subtype messages like destination unreachable, has a host unreachable, network unreachable, like 16 possibilities. We have a header checksum, and we have a data which varies according to the different type of message. There are some special conditions regarding ICMP. Most of them talk about error messages with ICMP. The first one is, and the most important one, is that no ICMP error message is sent for or sent in response to another ICMP error message. We do not want to have loops on the internet. If we have a fragmented, if we have fragmented IP datagrams, then ICMP error messages will always be sent for fragment 0, which is the first fragment. We will not send ICMP error messages for datagrams that are destined to a broadcast or a multicast address, and error sent in response to datagram sent as a link layer broadcast. We have other conditions. One of them, again, no error message are sent in response to ICMP messages. And another important one is when ICMP message of unknown type is received, we are gonna discard it. If we look at the list of ICMP messages and list some of those, we can see that with query messages, we have quite a few. Usually people just think about the ping utility and the ICMP echo request, but there are other query messages. There is the timestamp query message, which we use for network latency. There is the information request and the address mask request query messages used for net mask and address mask of the network the computers reside on. All the query messages were initially designed to work on the same network as the query host, as the source hosts for those queries. But apparently we can use them across the internet nicely. Error messages, we have the destination unreachable, source quench, redirect, time exceeded, and parameter problem. Source quench, if you're sending a host too fast and the information too fast, then the host will issue you back a source quench or message. Redirect will tell you, a router that sits on your same network will tell you to use another router on the same network for future routing to the host you try to route to. Time exceeded, you have two type of messages here. Whether the IP time to leave field value reaches 0, then the time exceeded error message will be issued. And when a host fails to combine fragmented pieces of the information you sent, you will get a time exceeded fragment reassembly time exceeded. The last error message is parameter problem, which will be issued when a field inside the IP header will have a bad content, such as if we will play, especially with 3 fields, the header length and the total IP length, and with the IP option, then we will get back a parameter problem error message. Just a quick review on those. We can use all the query message for host detection. Whether a host answers our queries, then he is alive on the internet and he is there. And we can use more advanced host detection error messages. If we're sending an offending packet that will elicit back an ICMP error message, then again, we can just find a host that issued the ICMP error message and he is alive. There are some dirty tricks with those error messages and packets that initiate those. If we are an attacker on the internet, we will look for a certain piece of information. We will look for what hosts are available for our attack. We will look for the services that are running on the host. We will use a port scanner to understand what are the open ports, and then we will try to fingerprint the operating system used by the host. All this information will give us a clear indication about the host, the operating system, and maybe a service which may be vulnerable to an exploit that we can use and to penetrate into the network. Again, ICMP is unique, usage is unique because we are using less and less traffic in order to get to those results. All the methods you will see in this presentation were discovered by me during my ICMP research. For active operating system fingerprinting, we can use 3 types of datagrams. We can use a regular ICMP query message, we can use a crafted ICMP query message, and we can use ICMP error messages. The first approach is the who answered what approach. This means that I query the host, see what he answered for which kind of query messages, build myself a table or a database holding this information, and then when I probe a host, I will try to correlate the information I get with the database of fingerprinting that I have. This kind of approach was very useful until Microsoft Windows 2000 family of operating system were launched. Linux and the BSD variants have used their default configuration to answer for ICMP query 2 types, ICMP timestamp request and ICMP echo request. Now, when Microsoft released Win2K, they do the same. They mimic the behavior of BSD, and if you'll see David LeBlanc, he will say, no way, we do not do that, but yeah, they mimic a bit of the behavior of the Unix operating systems, and I will show you and demonstrate later why I tell this, why I say this, and they'll do the same. We can use another question or a thing to build a database, which is a question which operating system will answer to queries aimed at the broadcast or the network address of the network they reside on. All the Microsoft-based operating systems, except for NT4, which has an SP less than SP4, will not answer for any broadcast attempt. Usually those operating systems will be Unix and Unix-like operating systems. We can map with this approach Ultrix, Linux, Sun Solaris, and HP and AX-based machines. We can have a 3-step, we can see here a 3-step diagram which describes this approach, one of the possibilities. First, we issue an ICMP timestamp request to the broadcast address we are targeting. Solaris, HPUX, and Linux will answer our query. We will take those IPs and query them with ICMP information request, again aimed at the broadcast address. We will see that HPUX-based machine will answer us, and Solaris and Linux will not. We'll take a 3rd step and just query those IPs with ICMP address mask request, a regular one aimed at the specific IP, the reply we will get from Sans Solaris, and Linux will not reply. Yes?
Has that behavior changed in Linux 2.4?
No. You can set it and change it, but they did not change that, as I remember. All those behavior types are default out-of-the-box installations, and sure, you have some options that you can disable those, but again, if your box answers for timestamp or information request aimed at the broadcast address, or answer for anything that aimed at the broadcast address, then you have trouble. Sure, the RC states that it is not an abnormal behavior to answer those queries. It also states that it may be silently discarded by a host, so this is not an abnormal behavior, and Microsoft behaves correctly. Well, with this one at least. One of my favorite IP header fields is the IP time to live field. We have to understand that we have basically two field values used here, or two numbers used with ICMP. This field represents the maximum time the datagram is allowed to travel on the internet. It was intended to be set as the maximum time this datagram will travel, so we will not have datagrams traveling all the time around the internet, and nobody will stop those. This field value will be decreased at each point that the the IP header, is being processed. It may be longer than a second for a device to process this datagram. So if you're thinking that this is something that will state how many seconds or how much time it took to a datagram to arrive from one point to another, then it's false. The RFC also states that the maximum value we can set this field to is 255, which is equal to 4.25 minutes. Okay, I talked about that as well. ICMP has two separate values. We have to remember that. Two separate values that are not the same, like TCP and UDP. One value is used for ICMP query messages, and one value is used for query replies. This unique field value helps us to identify certain operating systems and group of operating systems. This is as well the simplest way to fingerprint an operating system. If we will look at the ICMP query replies at first, we can see that the regular values that we will see will be 255, 128, 64, and 32. Now, those will not be the original assigned values to the datagrams that we will get back from the host we query, because along the way, some stations or some hops decrease this number. So how can we guess what was the initial number assigned to this value? We have those values I stated before, and if, for example, I will see 214 as the IPTTL field value, it will be a good conclusion to make that it was first assigned with the value of 255. There is a second approach that says that we can use traceroute or traceRT in Win2K in order to trace back to the host and know the number of hops between us and the target. This is only a good guess. We will see that some of the people in the security industry use this approach in order to passively map host. For example, when someone queries you, there is a unique IP TTL field value assigned, and they want to see What is the accurate value it was assigned at first? It was at 255.128.64.32. So what they claim is, you see the value you get, for example, 238, which is the IP time to live field value, which I got back from my box in Chicago in the hosting facility. You can try to hack it, but they kill you. So if you do a quick math, you take 255 and you take off 238, you get 17, right? So you say 16 hops I will have the gateway, right? Silence. Right? Okay, wrong. Why it is wrong? Here I take the traceRT command and states that it should be using 16 hops only to get back to my website. Now, as you can see, after 12 hops, I'm getting back to my website. Now, where are those 4 hops or 5 hops missing? Well, if you remember, a router may process the datagram more than 1 second. Or, in my case, I was in Israel and I traces back to the United States. So, when the packet traveled from the States to my house and from my house to the United States, it takes 2 different paths. This is routing. So, don't use that, especially if you want to passively understand who's the guy behind those pings you get. If we make a quick table, we can see that we have some unique values. Linux based on kernel 2.2 and 2.4 will use 255. Kernel 2.0 and DGUX, which is not stated here, will use 64. Other Unix variants will use 255. And if we look closely at a great implementation from Redmond, we will see Microsoft Windows 95 uses 32 instead of 128 as the other Microsoft-based operating systems. Now, if David LeBlanc was here, he was saying, yeah, but we released Win 95 like ages ago. So, what? Still, I have a valid point here. I have a unique operating system with a unique value, which I can understand. What is the operating system? I can also group the operating systems according to the initial values assigned. The Unix and Unix-like variants, the DGUX, which is now a compact true 64 and Linux 2.0, and the other Microsoft-based operating systems. This is simple. I'm just issuing ping from my box, and I just see this information coming back to me. It's not that hard to do. Now, we have this fun with the request as well. Again, the value we will see when we will see those requests hitting our IDS system will not be those who was first assigned to this field. So, how we can guess what was the initial value? Again, we know that there are some default values used. We can use those. Or we can use the faulty thing I just talked about here. Well, it's better to guess than to do the faulty thing. Now, especially if you are trying to passively fingerprint someone, then if you will hit him back, he will just understand that someone just understands that he is pinging, and he will stop and run away. Especially if this is a script kiddie with AOL connection, you will not see him again. Now, this message is passive. We do not need to do anything active. Now, the nice thing here, I will give you the great thing first, is the Win2K family. All the other operating systems which I have mapped, and there is a big list in my research paper, use other values. For example, Linux 64, Unix and Unix variants 255, all the other Microsoft Box 32, and here is Win2K with 128. Why? Someone has a guess? Come on. I don't know. Simply, 128 seems nice to Microsoft, so here is 128. Again, we can take this group and, you know, we have another group here with Linux and with the other Unixes and Unix variants and the other Microsoft-based operating systems. So if we look closely, we will see that with a regular Win2K member, we see 32 in the request, 128 in the reply. We see some other operating systems with unique values. So this is really a dumb thing which you can use in order to actively and passively fingerprint an operating system. Other stuff are more technical and, well, I had to think about them more than I had to think about the time to live field. We have on our IP header a nice field called the type of service byte. Before people will jump and say, yes, it is being now replaced by the diff-serve and quality of service stuff. But only Microsoft Win2K actually implemented this RFC, and all the other operating systems just using the old RFCs and still did not implement the quality of service yet. So we have three fields inside this byte. Processing field, which is used to prioritize IP datagrams. The type of service field, which describes how the network should make trade-offs between throughput, delay, reliability, and costs in routing those IP datagrams. And another nice little bit called the must be 0 bit, which I like the most. There are some rules which RFC 1122, which describe the host requirement states, and they are about the way these preceding bits should be handled. Well, it doesn't say anything. It only states that the DoD has a special meaning of the usage of these fields. Well, I asked the DoD guys on my training session, bless ya, and they did not know why they did just want this in the first place. RFC 1812, requirements for IP version 4 routers, states that an ICMP reply message must have its IP preceding field set to the value as the IP preceding field in the ICMP request that provoked the reply. I love the language, provoke the reply. Okay, but if we think about it, it has its logic. If we just want to prioritize something, what we want this packet or this datagram to come back fast as possible. Now, sure, I was thinking that it might be more than that here. This example with a tool called Syng, which is the Swiss Army knife for ICMP, developed by a Spanish guy called Andreas Alfredo Omela, is being used here. I'm sending 5 datagrams with the type of service byte set to 128. This means the first bit of the preceding bit is highlighted to a certain IP address of an X4.3 box. As you can see from the reply, the type of service which I get back is 128. This is all nice and well, but when I do the trick with a Microsoft Windows-based machine running a Win2K, then it all starts to be more nicer. See this? This is 0. Why is this 0? Well, according to Microsoft, they want to implement the new RFC, but I doubt it. We have another operating system who do the same, which is Ultrix. Yeah, I had actually found an old Ultrix box, and it really pissed me off to see that it has the same behavioral patterns as the Win2K. Did Microsoft look at the Ultrix to understand the behavior? I don't think so. To our rescue, there is the IP time to live field, assigned 255 with Win2K, and 255 with the Ultrix and 128 with the Win2K, rescuing us from this problem. We have as well changed patterns with this kind of ICMP query message type. Now, you have to understand that some operating systems implemented differently the different types of query messages. You've been thinking that if I have one query message, since we have so much fields that are alike, will be implemented the same. Well, again, you are wrong. If we look at this diagram, another three-step, amazingly drawn visual diagram which I have made, we'll see that if we are using ICMP echo request with the preceding bits different than 0, we can see that Win2K family and Ultrix will send us 0 as this field. Again, we differentiate in between those two, as I explained before. If we will send an ICMP timestamp request with this preceding bit set to a number different than 0 to the other IPs of the operating system we wish to understand what they are, we will see that Windows 98, 98SE, ME, and Win2K now will reply with 0, as well as the Ultrix box and OpenVMS. Now, since we know that Microsoft Windows 2K from this step, and we also understand what is an Ultrix box here, and we can use again the IP time to live field, we see that we have the OpenVMS here and the other group of 98, 98SE, and ME here. Now, the last step will be sending an ICMP address mask request to those machines, identifying Microsoft Windows Me and the 98 and 98SE group of operating systems. Again, this is a three-step diagram where I have identified Ultrix, Microsoft Win2K, OpenVMS, WinMe, and Win98, 98SE. Simple. So, we have another two fields here. We just cannot let them without any check. The type of service field has its own way of usage. It relates to error messages, query messages, and reply messages. There is strict rules saying what we should do with each of one of those messages. Error messages should always be sent with the default type of service. Request messages may be sent with any type of service value. And the reply messages should be sent with the same value as the type of service field that it was corresponding in the ICMP request. Well, it is nice to see that there are rules, and again, if we will look closely, we will see some of the operating system violates those. This example was produced against the FreeBSD 4.0 machine, again, with Sting. We see that I have sent a valid type of service field value, which is 8, and I received it back from the operating system. If I have sent here a non-legit type of service value, it echoed it back as well. As we saw before, Win2K has a unique interpretation. And again, this was the case with these bits. Again, I'm sending a type of service field value of 8 and receiving 0. If you look again at this, again, three-step diagram, we can see that Ultrix and Novell Network has the same behavioral patterns as Windows 2K family. We can do We can divide those according to the IPTTL and identify all tricks. And again, use another trick here, which is ICMP timestamp request, which the win box will reply and the novel box will not. Novel also answers for ICMP echo request, and that's it. With the other group of IPs we have, excuse me, we can send an ICMP timestamp request, again with a value different than 0, and guess what? 98, 98AC, and me will reply with type of service 0. We can then again send another ICMP address mask request and map between 98 and the me boxes. The last field within this byte is the unused bit. Well, sure, should be 0. Nobody will set it up, but again, why not setting it up and see what happens? With Unix and Unix variants, as we can see here with FreeBSD, sending this bit lighten up will end up with getting him back. Is this normal? I don't know. If this according to RFC, RFC is not stating the accurate behavior here, but you have expected that this field will not be echoed back and will be 0. Win2k again will zero out this field on the reply. Ultrix, our friend, will do the same. So how can we differentiate? Again, according to the IP time to live field value, we can differentiate between Win2k family and Ultrix, and again with some other steps, we can have OpenVMS, WinME, and Win9898SE. Now, when Microsoft released Win2k, someone from Microsoft stated that they were trying to do a better job at hiding their operating system. Now, if you will meet David LeBlanc, he will say, no way. But we cannot argue with the facts. They were trying to make Win2k a bit harder to understand what it is, and all those methods just highlight Win2k out. Why this type of service byte is so hard or its behavior is not that good with Microsoft? Well, I guess because of this registry value. If we look at the default TOS value, it is set to 0. There is no way to set this to something that comes in. It just stays 0, or you can set it to a value between 0 and 255. We can override and overwritten this registry value if we will set the IP underscore type of service option, as long as the disable user type of service settings is not set as well, or by enabling the quality of service policy on Windows 2K. So apparently nobody at Redmond just bothered to read the RFC. Another nice thing we can do is setting the don't fragment bit with our requests and see what happens. Will the operating systems that we query will set this bit and echo it actually back to us. If you know, there are 3 operating systems that will set the don't fragment bit on default when you query them. Those are Sun Solaris, AX for X, and HPUX with a little twist. So I was thinking, if other operating system echo other fields, why not trying this one? This one is a bit more tricky. Again, we just lighten up the DF bit with the ICMP echo request. The operating systems which do not echo back the DF bit, and they should not, if you think about it, they really should not echo back, are Linux, Ultrix, and Novell NetWare. Linux and Ultrix vary in the IPTTL field value, and again, we can set them away. And we have Novell as well. The second step we will do the same trick with just this time with ICMP address masks. Now, the operating system that will not echo back the DF bit will be Windows 98, SE, and Ultrix. So we have all those operating systems mapped. The last trick here is to send the DF bits with the ICMP timestamp this time. We'll have Linux nearly, well, Microsoft Windows 98 SE, ME, 2K, and Ultrix do not echo this value. Now, we identified Linux, Ultrix, Novell, Win 98 SE, and Ultrix previously. Then it will leave us with Microsoft Windows ME and Microsoft Windows 2K. But if you look closely at the replies, if you remember, Win2K will give us the value of 128 as the IP time to live field value. And again, we can differentiate between Microsoft ME and Win2K. Basically, we map 98 SC, Microsoft Win2K, Microsoft ME, Linux, Ultrix, and Novell Network. 3 steps just required. The next thing I'm going to speak about is what I call the ultimate who is a Windows box machine test. This was actually my first pass to BugTrack a long time ago. Apparently Microsoft were not thinking this is worthy to change. RFC states that when you send an ICMP echo request, all you need to do when you get the request to your box is to change the type of message to ICMP echo reply. This means to change the type of message from 08 to 00, recalculate the checksums, and send the reply back. Now, I wanted to be nasty. I took the code field and changed it. I just put a value 26 hex instead of 0, sent to a Linux machine, and I saw that they comply with the RFC. This was nice, but again, with the Microsoft Windows operating systems, they have their own unique behavior. I call it I play God behavior. Why sending an ICMP echo reply with a code field set to a value different than 0? This is the answer I got one day. Well, who tells you how to do that? RFC states, change the type, recalculate the checksum, and send it back. You do not have to validate the ICMP echo request. It's simply not your job to do. Well, again, they had their own reasons. So, all the Microsoft-based operating systems, nevertheless, whatever they have there, which we can say 95, 98 SE, Microsoft ME, 2K, 2K-SB1, all those hotfixes, blah, 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 will do the same. All Unix and Unix-like operating systems, networking devices, will leave this code field set to the value, will send them, which will make Microsoft-based operating system alone in the world with this kind of behavior. Now, if you think about the stuff I've shown you until this point, you can do combo datagrams as well. Just let me finish this one. With ICMP timestamp request sending the code field different than 0, I had a revision or a revelation, I have to say. No reply with a regular timestamp I will get from 95 and NT4 machines after SP4 and with SP4 and above. Other operating systems, if they are not configured otherwise, will out of the box will answer. Now, look at this. I will send a timestamp with a code field different than 0, and suddenly all those nice Windows boxes will not send me a reply. Someone got an answer for that? Microsoft do not have as well. So I'm asking why this happens. It is an inconsistency, because if we are having ICMP echo replies and timestamp replies, you think that all the IP header and most of the ICMP portion will be the same. So if you build your own programs, then if you have similarities, then you will be happy because you have much less code to deal with. Well, apparently not. This is a Uber mass scheme that works with what I call DF bit echoing with ICMP error messages. All I have spoken about until this point was query messages and their unique replies. Well, you can see much differences between one operating system to another if you are looking into ICMP error messages. You will see that some of the fields are not being echoed correctly by the operating system, which is the target of your offending packets. If you know, an ICMP error message has to have the offending packet's IP header and at least 8 bytes of the offending message. Well, this varies as well. If we send a DF bit with an offending packet, then error messages which will not echo the DF bit will have listing Linux, Ultrix, Novell, and all those blah blah Windows-based machines. Now, if we look at the echoing integrity of those machines, we will see that Ultrix will have the wrong IP ID and the IP header checksum is 0 and the original checksum is 0, so it will make a unique distinctions about Ultrix. Linux will think he is a router, and this is the thing I'm not understanding, and will set the preceding bit's value to C0 hex. If you remember, one of the first slides states that RFC 1812, which is the router requirements, tells that a router should set its value to 6 or 7. Well, I've asked if Linux is a router, and still I haven't got any answer. Well, he is a router if you will enable his routing capabilities, but other than that, he is a simple host. If we look at other stuff, we will see that if we send a message with more than 8 bytes of offending data, then some operating systems will quote more than 8 bytes of the offending packet's original data. Now, HPUX will stop at 64, while other operating system will quote more. Now, we're left with Novell Network and those nice Microsoft boxes. If we will send an offending packet that will elicit an ICMP time exceeded error message, Novell will reply with echoed IP time to live field value 0. Now this is an implementation error because this is not the error message we wish to elicit. We were talking about fragment reassembly. This thing is talking about fragment reassembly. Well, I send 1/2 or just one piece of a datagram I want to send, and I will look for the reply. Now, when Novell replies for this one with the ICMP fragment reassembly error message, it's mixed up between the time exceeded with the time to live field value and send you instead the type correctly about the fragment reassembly time exceeded, but the time to live field value suddenly becomes 0. Now, if you want to fingerprint Novell, you use this dirty trick and you fingerprint each Novell Network operating system box that run on the internet. So I'm going to Novell Network's website and saying, okay, there is support at novell.com, sure, right? Sounds good. No address. Okay, security at novell.com, no one there. Information at novell.com, no one. Okay, so I'm looking into some people that are Novell-centric that will help me send the bug to Novell so they can fix it. So nobody really understands who's the man in Novell that do security. So eventually I sent it to someone, and I think it's 3 months that I'm waiting for Novell to say, okay, we have a problem, but I guess it's not a priority there anymore. The other group of operating systems will be all the Microsoft Windows based. This is a bit complex two-step process, but eventually it will give us again all the Microsoft based operating systems. And if we will look again at the IPTTL, we can just take out Win2K again here and differentiate it between NT4, 9898 SE and me, and Win2K. Before I go into passive operating fingerprinting, which is the new information that I just saved for Black Hat, I just mentioned that we can use a combo ultra-hexer, ultra-mapping datagram. We can use a lot of stuff together and just send one datagram with it. For example, we can set the DF bit and change the code field and do other dirty tricks such as change the value inside the type of service, and according to the reply we will get, we will have a clear distinction between the operating system. Just combine everything, send it out, show it is crafted, but hey. Now, we can use for example, the type of service if we say that we use, for example, quality of service. Nobody will be suspicious that we're just faking it. Or if we will set the DF bit with our queries, nobody will figure out if we are really a Sans Solaris, HPUX, or an HBox, right? Nobody can say that if we just fake it. Well, we have some stuff we can use passively in order to map a targeted network and networking host communicating with it. This technique is called passive fingerprinting. In the open source field, it's quite new. There are some quite nice papers written on this subject. I think I've listed some at the end of the presentation. And again, different operating system will use different implementation of the TCP/IP stack. We will identify those differences, and then we can state what is the operating system, and hopefully we can have a clear distinction. We'll ask a few questions here. First, which operating systems answer for what kind of ICMP query message? If we see those query and reply messages flying by the SNF network we're residing on, we can do that. It will give us a nice understanding, not more than that. We will not expect someone to use all the methods I've stated here and give us the treasure. We can also see which operating system answer for spatial or crafted ICMP queries and how they did that. Again, only if people will use the methods I have introduced here, then again, we will see that. We can also look at ICMP error messages. It will be even better because ICMP error messages will be sent for a lot of error conditions. And we can do an analysis of error messages and query messages. Now, query messages are fun. If you look at each operating systems, or you go on to look for something that will send you an ICMP echo request on each operating system you will examine, you will see that each operating system should have and implement an end user accessible application interface for sending ICMP echo requests, query messages to other hosts. Well, if you will look, the ping utility will use this implementation on the various operating systems. An important note is that ping might use its own default values for several fields within the ICMP echo request datagram and not the operating systems. This is especially true for Unix and Unix-like operating systems. While we will see that Microsoft-based operating systems, we have really fun with those. Since not all the ICMP query requests are implemented on the various operating systems, I have decided to look at the query messages and to use the different ping implementations in order to passively map between operating systems. Which fields we have that we can use in order to do so? We have the type of service byte, which includes 3 fields. We have the IP identification, which until now nobody even looked at it, I think. The DF bit, the unused bit, IPTTL, and IP options, which is the IP portion of all of this. Now, only if someone will set the type of service byte, then it will help us. Only if someone will set the DF bit with its request, then we can say, okay, there is a central areas, an X, and HPUX group. If someone will use the unused bit, we'll know that this one is crafted. IPTTL will be much of a help here, and IP options will be the same. But if we look at the ICMP portion, we will be more than happy to discover that we have some excellent stuff to work with. ICMP ID, ICMP sequence number. Now, RFC states that ICMP ID should help us to differentiate between a stream of ICMP query messages sent to one host and to another. This means that one host will get assigned one number and the other will get assigned another. The sequence number will help us to differentiate between a stream of ICMP queries aimed at the same host. This means that the combination of ICMP ID and ICMP sequence number will help us to differentiate between the ICMP datagrams. Questions? Okay. We can look at the ICMP data field. The RFC states that the amount of information we can put inside this field is implementation choice. We can look at actually at 3 things here. Offset from the ICMP header, the actual content of this field and the size of this field. And if we will look at the size, we will look at the total size of the ICMP request. Now, if we will look at the Linux ICMP echo, if we will look at the ping utilities ICMP echo request that was compiled under Linux from the IP utils package under Red Hat Linux with kernel 2.2.14, we can see that we can learn some information from just the information we get back from the operating system that we queried. For example, if you remember, the time to leave field here should state that I'm pinging a host on the same network I reside on, and that host is a Unix or a Unix-like operating system. I can also see that I'm sending 56 bytes of data that makes the total size of the datagram of 84. I can also see that somehow ping calculated the time it took for the datagram to reach its destination and to come back. I can see it here in the round trip minimum, average, and maximum times. Now, if we will send 2 ICMP echo requests, one after the other, which if you think when you do use ping utility, you just hit ping, whatever, and don't bother to state the amount of echo requests you wish to send, the amount of datagrams, we will see several differences. We can see that the IP time to live that was used is 64, type of service 0, ID 383, ICMP ID is this number, and the sequence is 0. I can tell you that the first 8 bytes here were used as a timestamp in order to calculate the round trip time. This means when I send you the ICMP echo request, my operating system or the ping utility stamps this timestamp, and when I receive back the reply, it was echoed back to me, since the RFC requires that nothing will be changed in the data portion. and I can calculate the amount of time it took for this datagram to travel to the other side and come back. Another interesting thing to see is what is the actual data inside my datagram. Here we can see all those symbols and numbers, which actually starts right after the timestamp, which is here. Just 08, 09, 0A, 0B, and so on, which compiles this. If we are looking at the second packet, what we can see that is changing, this is a nifty trick if you see it, put it in the same place. We can see that the IP ID was changed. Now, if you look closely, you'll see that there is a 3-number gap between one and the second IP ID. I can tell you that with Linux, the IP ID gap is 1. What was else changed was the sequence number. The sequence number gap is 100 hex, which is 256 decimal. We can also see that the same ICMP ID was used for both pings, for both ICMP echo requests. If we examine Microsoft Windows 2K Server, which ICMP echo request, we can see other nifty stuff. We do ping, we use the ping.exe utility on Windows, which is something Microsoft has built and Microsoft is responsible for. They come to hijack me from Microsoft. We see that again, we can see the time it took the datagram to travel to the target and to come back. We see the approximate round trip times, which are really nice. 0 millisecond is really fast. Really on my local network, it's really good. I think it's a world record. We should send this to Guinness. Now, if we look closely, you see that in the reply, the replying operating system, which is my Linux home box, answered with 255, again, the IPTTL field value of the Unix and Unix-like. If we want to look at the trace, and here I'm using an older version of Snort, which I recommend to upgrade immediately to 1.7, we can see some other stuff. First, I will look at the data portion. Now, the data portion starts with 61, which is hex equivalent to A. Now, you think Unix was using the first 8 bytes in order to put the timestamp, right? So where did the timestamp go to? Question, someone can answer? This has a really good answer. Into the memory. Should have been written somewhere in order to provide me with the information, right? Something has to be written in order to allow the operating system to tell me that it took the amazing time of 0 milliseconds for this datagram to come back. Other stuff that we can see here is IPTTL 128, I stated this before, IP ID 279, ICMP ID 512, looks a bit suspicious. Sequence number, this number, and it is an echo request. If we look, again, we'll do this trick. Yeah, like this trick. We'll see that the IP ID here, the gap is 1. The gap is 1. And the sequence number, again, change, and the gap here is 256. Okay. What did not change is the IP ID. You think, okay, IP ID should be the same, right? No problem. If we're looking again at Microsoft Win 2K server with SP1 installed, and it is important what is the version of the server, as I will tell you in a couple of minutes. We use WinDump. I use the, I think it was 203, written by J.D. Glaser of, in the time he was in anti-objectives and not in Foundstone. and dumped what I've got. What I've got back is, again, here I've got an IP ID, which is 768 decimal. If you remember here, I got from a Win2K without the SP ICMP ID of 512. Now, here I get 768. Well, I was a bit suspicious about this. So here I am pinging one operating system, one box with a certain IP, and here I am pinging another. So you were thinking that the IP ID must change, right? Because the IP ID helps us differentiate between different machines. Well, no. Microsoft will use ICMP ID as a constant number, regardless of what we will do. Now, it will rely upon the ICMP sequence number to differentiate between each ICMP echo request whenever it was sent to. Okay, I was a bit suspicious, so I went and looked at the ICMP echo request with WinNT with SP6A installed on. What I saw here is the TTL of 32, ICMP ID 256, sequence number 256, and this nifty drifty IP ID. Now, if you look closely at the IP ID, you will see that there is a gap of 256 between one IP ID and another. Well, if you remember the Win2K machine, it was the gap of 1. Now, you'll say, yeah, you might not be getting the accurate or the one gap between one packet to another. Well, right, but if I will have two packets coming from the same machine, if it's not above 256, I can say 100% it came from a Win2K box. Now, looking here, the sequence have started with 256 and the ICMP ID was 256 as well. So we have basically the gap of the IP ID, we have the TTL we can use, we have the ICMP ID here, and we have the sequence number. We also have, regardless to other operating system, the data field. Now, we can forge the data field quite easily if we just play with one of the ping options and state which kind of data we want to enter. If we look closely at those nice operating systems, and then we will look at the IP ID, and it took me a while to understand that there is actual distinction here. Unix and Unix-like operating system, IP ID gap will be 1. Windows, except for the Windows Me and Win2K family with 2K and 2K SP1 will use 1 as the gap. Now, if we will look at a bigger table describing all the different values assigned to those fields, we can look at and see sequence numbers with Microsoft Windows-based operating systems will always start with 256, which is 100 hex. Now, with Unix and Unix-like will start with 0. The gap between one sequence number to another will be 256 with Microsoft Windows boxes and with Linux and FreeBSD boxes, while AX and Solaris and other Unix variants will use the gap of 1 hex. Another nice thing to know about is the ICMP ID field value, which starts with a certain number. If you look at the ping utility with Unix, you will see that the ICMP ID is actually the process assigned to ping when you run the command. With Microsoft-based operating systems, those values are constant values, and we can just differentiate between the variant operating systems. For example, until SP1 was released, Microsoft Me was the only operating system among the Microsoft-based who was using the value of 768. Now with SP1, Microsoft changed the behavior. They were using 512 as the ICMP ID field value for the Win2K family, they went and changed it to 768. So I was like asking Microsoft guys, why you guys have changed that? And the answer was no answer. Now if you look closely, we can differentiate between 98 SE boxes and NT boxes. And even we can differentiate between 2K and 98 and 98 SE because of the IP ID gap. We can also see that the ICMP ID will be changed when we are talking about Unix and Unix-like operating systems. And with Microsoft Windows, this value will be constant. This is an implementation problem. This is an RFC misunderstanding. And I had one of the MS guys telling me this is wrong. It took me an hour to convince him, and we were shouting. Now, this thing was discovered 3 days ago when I installed my lab for the training session. This was actually something I did not understood when first Jeff Moss and Keith there installed a multi-home Win2K machine for me. Now, I asked them to ping me from that Win2K machine so I can see if all the information I have found correlates. And oops, I saw that the ICMP ID was not 512, it was 256. There is 2 network cards inside that machine. So I asked them to remove one of those cards and to ping me again. Well, guess what? 768, because it was SP1. So we are like kids, putting back the Ethernet card, pinging again, 256. Take out the card again, 768. So, as you can see, we have a nice method in order to differentiate between a multi-homed Microsoft box to not a multi-homed box. You can see that this actually gives you other kind of information. If you see ICMP ID 256, IP ID gap 1, here you go, Win2K multi-homed machine. Now, it might be the same with other variants of Microsoft with multi-homed network cards. I did not have the time to check it since I don't have my lab here and it was 2 days ago. But think about the possibility of identifying multi-homed machines by just, looking at that variant of operation, just looking at this change, and here we go, we have a gateway. What is that? What Microsoft has? Oh, proxy server, ISA server, or whatever I can do server. So you can identify multi-home gateways. This is another thing I talked about with David LeBlanc. Sure, Microsoft can fix some simple stuff that I have found which are not corresponding to the RFC, which do not correspond to nothing, but simply they have their pride and they will not come and say, yeah, we were wrong. I mean, if you look at the ICMP ID thing, it's like, where you guys took that from? Why do you are doing this? And they even don't have the answer for that. Eventually, each machine, each operating system will have its own IP stack differences from one to another operating system. This is correct. But if I can do that with less traffic and if I can do that more efficiently, then why use Nmap if I can ping? So, you have here further reading. If you really wish to read all the RFCs, you are more than welcome. If you are developing something, then the RFC is your friend. You can get all the RFCs from the IETF org. Version 3 of my ICMP usage and scanning paper will be posted in 2 weeks to my website. The guys who were in my training has a final, well, not that final draft of it. These are some links to the tools I have used in this presentation. I highly recommend them if you want to test your systems, applications, especially Sing and HPing2 will do nearly everything for you. You can use Snort as your sniffer and intrusion detection system, even if it's not that perfect, but it will give you a lot of stuff you need, and it was improved from version 1.6 to version 1.7. I'm a bit proud to say that some of the stuff I asked for from Marty Roche were inserted. If you have questions, this is the time. Going once, twice.
How about Macintosh?
You love Macintosh? Enjoy your time, my friend.
ICMP fingerprinting with Macintosh?
Well, if you'll take Jeff's girl Macintosh machine, it will be more than delightful to do that. Thank you for your question, Keith. Yeah.
Actually, regarding the extra Ethernet card and MC, did you try a third Ethernet card?
Well, I was thinking of putting cards until the machine will blow up. It was kind of interesting to put a quad card inside. I'm trying to have all the gear for doing that since I'm just having 2 computers at home. It's a bit of a problem. Something I didn't state is that this whole research is being done on my spare time. So, yes?
Do you expect any difference between Ethernet-based ICMP traffic and dial-up-based?
Not that I have seen. Sorry? The question was if I will expect to see differences between ICMP, between dial-up connection and an Ethernet card. If you think about it, it's just the physical layer. It shouldn't be a problem with it. But again, if you look at the Microsoft case, then I don't know what those guys were thinking about. One of the options is routing, but again, if you have the IP, then I mean, I don't think of anything that is worth doing so. Any other questions? Thank you. I enjoyed being here. Thank you for your time.